All right, guys, so we're going to go over the last unit review before our final review. So this is the Unit 5-6 review. I'm briefly going to go over this periodic table real quick just to determine charge and things like that. So it would be really helpful if you had one handy to look at while we're going over this review. So I'm going to try to save some time, not scroll so much back and forth. Okay, so looking at the periodic table, big thing on this test is you need to know how to determine charge. Okay, so the oxidation number of an element. Okay, so the way we do that is simple. We just look at the top of our groups. Okay, so remember the perfect number of valence electrons was 8. Okay, so over here on our noble gases, right here, it has 8 valence electrons. So it does not need anything else. So it has a charge of 0. So that's a starting point right there, just to start there with 0. Next one has 7 valence electrons, so it's missing 1, so that's going to be a -1. Okay, 6, it's going to be -2, and then -3, and then plus, this can be plus or -4, so this can kind of go both ways. Then we have 3 valence electrons here, so the odds of it finding 5 more are not going to be very likely, so what it's going to do is just going to give up those 3, so it's basically saying, hey, I have an extra 3 right here. Okay, then we're going to jump across our transition metals, okay, over here to 2A. So this whole group right here is going to have a charge of +2, and then lastly has a charge of +1. Okay, so that's going to be a big help on this test. If you do not know how to find charges, I would highly recommend practicing that. And then basically in this D group here, so starting right here in this D group, going over to the staircase, we have our transition metals that are going to vary in charge. Okay, so those can be anything, except for there's a few exceptions. We have silver, which is going to be a +1. Zinc is going to be a +2. And aluminum is going to be a +3. Okay, so those are your exceptions. So those are the 3 that do not need Roman numerals. You do have lead and tin right here. So lead and tin can either be +2 or +4. It would still need a Roman numeral, but those are the only 2 options for those 2. Everything else besides silver, zinc, and aluminum will need a Roman numeral if it falls into that transition metal area. Okay, so let's get started on the review. Okay, so again, I would have your periodic table handy on you, so I'm not scrolling back and forth. So if you were to look up cesium on the periodic table, it has a symbol of CS. Okay, and it's in the group 1/1A. Okay, so that first group on the left. So that means it only has 1 valence electron, which gives it a +1 charge. So the ion symbol is just the abbreviation. So cesium is CS, and then it would have a +1 charge. Okay, so that's your ion symbol. The ion name, so remember when we were putting names, when we were bonding, your cation's name never changed. So your cation is your positive one. So the cation's name never changed. The ion name would just be cesium. Okay, and we already talked about this. It has a positive charge, so therefore it is a cation. Okay, if you look up strontium on the periodic table, SR would be strontium. Okay, and that is going to be in group 2/2A. It has 2 valence electrons, basically giving it a +2 charge. So its symbol would be just SR with a +2. Okay, it's a cation, so I'm going to go ahead and write that because it has a plus charge. So that means our name doesn't change. So it's just strontium. Okay, Br is going to be bromine. Okay, bromine is going to fall into that group 17/7A. Okay, and where I'm finding these is right up here, the 17/7A, so that's right here. Okay, so let me kind of clear some of this up. Okay, so that's the group name on top. So 17/7A, it has 7 valence electrons. Okay, so it only needs 1 more, so it's basically missing 1. So that's going to be a -1 charge. So our ion symbol is going to be Br with a minus charge or -1, either way. So when we do our names, when this is an anion, okay, anion has a negative charge. When it's an anion, we end it in "ide." So this would not be bromine anymore. This would be bromide. Okay, so we're going to go to the next. So boron is abbreviated letter B. That is in group 13/3A. Okay, it has 3 valence electrons, so it has an oxidation number of +3. So this is going to be B with a +3. It's a cation, so we're not going to change its name, so it's just boron. And we already talked about that is a cation because it's a positive charge. So P is going to be phosphorus. Okay, so phosphorus is in the group 15/5A. Okay, and so it has 5 valence electrons. So that basically means it's missing 3. So it has a -3 charge. So this is going to be P with a -3 charge. And this is going to be phosphide. So it is an anion, so we got to change the name to phosphide. So this is an anion. Then we have oxygen, which is abbreviated O. Okay, oxygen is in group 16/6A. It has 6 valence electrons, which basically means it's missing 2, so we have a -2 charge. So it's going to be O with a -2. So it is an anion because it has a negative charge, so therefore we're going to change it from oxygen to oxide. Okay, so a couple more. So we got iodine. That is going to be I. That is in 17/7A. Has 7 valence electrons. It basically says I'm missing 1, so that's a -1. So this is going to be an I with a minus charge, or you can put -1, either way. So this is an anion. So this is no longer iodine. It's going to be iodide. So it is an anion. And lastly is going to be lithium. That is Li. That is in group 1/1A. And that is has 1 valence electron. So it's not going to find 7. So it's going to have an extra 1. So a +1 charge. So we're just going to write our symbol now. So this will be Li with a plus charge, or you can do +1, either way, doesn't matter. Okay, it's a cation. It has a plus charge, so therefore we're not changing the name, so it's just going to be lithium. Okay, so again, you can fast forward as much as you want through this video. If you get to a point where you're comfortable with anything, feel free to fast forward or rewind if you need to see something again. Okay, so we're going to go over the periodic table again. So group number, period number, and element symbol. So real quick, going back to the periodic table, a group goes up and down. And then you have your period, which goes left to right. Okay, so you can use groups. So 1A, 2A, 3A, 4A, 5A, or the 13/3A, 14/4A. Those are your groups. And then these numbers on the left right here, these are going to be the period numbers right here. 1, 2, 3, 4, 5, 6, 7. Okay, so that is your period number. Okay, so if we were looking at group 1A, period 5, so group 1A, so we're in that first group on the left, and period 5, so that would be rubidium right there. Okay, I'll just do one more, and then you can use your periodic table to kind of look along with the video. All right, so we need to find carbon. So we're going to find C. C is right here. So it is in group 14/4A. And if you look all the way over to the left, that is in period 2. Okay, so that is 14/4A. And that was in period 2. Okay, so you can use your periodic table for the rest of them. So if you look up krypton, that is going to be in group 18/8A. So 18/8A, and that is going to be in period 4. Okay, so next one, 16/6A, and then period 3. That is going to be sulfur. Okay, then we're going to do calcium, our last one. So if you look up calcium on the periodic table, that is in group 2/2A. And then it's going to be in period 4. Okay, so feel free to rewind that or fast forward if you need to. All right, so now we're going to go on to metals, nonmetals, and metalloids. So we're just going to talk briefly about this. Okay, so metals are going to be on the left side of the staircase. Okay, and it is going to be except for hydrogen. Oops, excuse me. Except hydrogen. Okay, and so what I'm talking about, the staircase, is on back on your periodic table. This staircase that goes down right along here, that is going to be that defining staircase. Okay, so now let me clear some of this up. Okay, so your metals are on the left side. Your non-metals are going to be on the right side. And then your metalloids are going to be the ones that follow right along that staircase. So they're the ones that are touching the staircase. Okay, so they're touching the staircase, but there's one exception, except aluminum. Sorry, I cannot write today. Except aluminum. Okay, so now we're going to talk a little bit about the properties of each. So metals, just like you would think, metals are going to be shiny, hard, ductile. Ductile just means basically you can draw them into a wire. You can use them as a wire. They're malleable. Malleable just means you can mold them, bend them, things like that. And then conductive. Conductive you use for electricity, so how well they're used for electricity. And then lastly, they're going to be solid. Okay, so these are just some basic properties. So non-metals are going to basically be the opposite. So they're going to be more of a dull, not shiny, soft. They are bad conductors. Okay, so not good for electricity. So bad conductors. Non-malleable. So not good at bending, anything like that. Okay, and then some of them can be solids. Some can be liquids. And some are gases. Okay, so basically what you would think of as a non-metal. And so kind of bear with my handwriting on there. And then lastly, properties of metalloids. They kind of have properties of both. Okay, so they can have a metallic luster, which basically just means shine. So they can have a shine like a metal. They're brittle. And they can be semiconductors. So not the best at electricity, conducting electricity, but they can be used for it. Okay, so they kind of fall right in the middle. So examples of metals would be anything left of the staircase. So that would just simply be something, you could just pick anything. Magnesium, calcium, silver. Non-metals are going to be on the right side. So you could just say chlorine, oxygen, phosphorus. And then anything that falls along the staircase that touches it, except aluminum, would be a metalloid. So that would be like things like silicone, germanium, arsenic. Okay, so big thing is metals on the left side, non-metals on the right side, and metalloids are just what is touching the staircase. Okay, so now we're going to look at completing the following table using the periodic table. So again, I would have that periodic table ready. So we can briefly go over electron configuration again, just to kind of touch base on it. Okay, so going back to the periodic table. So remember we had our groups 1s, 2s, 2p, 3s, 3p, yada, yada, yada. Okay, so we're going to be seeing that again. So let's see what example we're going to be doing. So we're going to use neon. So this is the noble gas shortcut. So we're going to start at neon, go to 3s2 and 3p4. Okay, so neon's right here, so that's where I'm starting. Then I'm going to go down. I'm going to go through 3s2, and I'm going to land on 3p4. 1, 2, 3, 4. So that means sulfur right there. So that is where I landed. So sulfur. Okay, so my element is going to be sulfur. And if we go back and look at the top, sulfur is in group 16/6A, and it is going to be period 3. So 16/6A and period 3. Okay, so the rest of them, I'm gonna go over them, and you can kind of watch along with your periodic table. So if you look up argon 4s2, 3d10, and 4p2, you're going to land on germanium. Okay, and if you look at germanium, it's going to be in period 4. So look at your left side. And then if you look up above germanium, that's going to be in group 14/4A. Okay, so now we're going to look at iodine. So this one I'll do for you. So iodine. So let me clean this up a little bit. Iodine's right here. Okay, so we're going to do the noble gas shortcut. So my last noble gas is going to be krypton. So I'm going to put krypton in brackets. Then I'm going to go down here to 5s2. I'm going to go all the way through 5s2. Then I'm going to go all the way through 4d10. And then now I'm back on 5p. 1, 2, 3, 4, 5. So I end on 5p5. Okay, so that was krypton in brackets. That was the last noble gas before it. Then we went through 5s2, all the way through 4d10, and then 5p5. Okay, that is in group 17/7A, and that was in period 5. All right, potassium, you're going to look at potassium on the periodic table as abbreviated letter K. Okay, so just in case you need to see that, K. So that would just simply be argon would be the last noble gas before it, and then it would land on 4s1. So that one's pretty simple. So that is in group 1/1A, and then that would be period 4. Okay, so now let's go over some of the causes, the factors that cause periodic trends. Okay, so a lot of these are pretty self-explanatory once we go into them, so we're going to make sure we explain them pretty good. Okay, so Coulomb's law, all that is it determines the force between charged particles. Okay, so we also call this attractive force. So this would be like something you would feel whenever you put two magnets close to each other. You're feeling that attractive force. Okay, but the main thing is it depends on distance. So it depends on the distance. I'm going to underline that. Depends on the distance between the nucleus, which is positive because it has protons in it, and the electrons. Okay, and they are negative. Okay, so just like a magnet, you take a positive in and a negative in, they're going to be attracted to each other. So the way I like to explain this is if you hold two magnets close to each other, okay, you feel that pull. Now, when you start to pull them further apart, you're increasing that distance. So therefore, you're not going to feel as much pull. So the further the distance, not as much pull. So there's not as much attractive a force. The only way to overcome that, so to overcome distance, okay, your charges would have to increase. You'd have to basically get bigger magnets. So I know I'm using magnets as an example, but this is the same thing that's happening between a proton and electron. Okay, so they're attracted to each other. So if we move them further apart from each other, they're not going to be as attractive. There's not that much pull. Which takes us into our next one. So effective nuclear charge is just simply nuclear pull. Okay, you have the nucleus, which has protons in it. So protons are going to have a positive charge. Basically pull on the outer electrons. So pull on the electrons, which have a negative charge. Okay, so as you go across a period, so remember period is what going from left to right. So as you go across, a period, the number of protons increases. So number of protons increases. Okay, so once we increase those protons, we're adding a more and more positive charge, so it's going to pull harder on those electrons. So which pulls harder on the electrons. Okay, so that's all that basically is nuclear pull, is the pull from the protons on the electrons outside. Now shielding is when we start getting more and more electrons. So when you have more and more negative particles, they don't want to be around each other. So they're going to kind of push each other away. So that is when, so shielding is when inner electrons will shield valence electrons. So remember, valence was outer. So it will shield valence electrons from the nuclear pull. Okay, so there's too many electrons in between the outer ones and the nucleus to get in the way, and so those outer electrons don't really feel that pull from the nucleus. Also, when you get a lot of negative things around each other, they want to push away from each other. So the valence electrons are being repulsed. Repulsed just basically means pushed away further or get away further by the inner electrons. Okay, so the more electrons I have, okay, the more they're going to want to get away from each other. Okay, so as you go down a group, okay, we're getting more and more energy levels, so more electrons leads to higher repulsion, which makes the electron cloud bigger. Okay, so as we're going down a group, we're adding more and more electrons, more and more energy levels, and those electrons are pushing further on each other, so it's making our electron cloud go out further, which makes our size of our atom bigger. Okay, so now let's actually go into the atomic trends. So atomic radius is just simply the size of an atom. Okay, so as you go across a period, it decreases. Okay, so we kind of talked about that. The more protons you have across a period, the more positive charge, so it's going to pull those in tighter. And then as you go down a group, it's going to increase. Okay, so what causes these trends? So as we go across, we have increased protons. I'm going to kind of go outside the box here. Increased protons pull the electrons closer. So we're not really adding any energy levels. We're on that same energy level. We're on the same period. So we're not really adding more levels, but an increase in protons is going to pull those electrons in tighter. Then as we go down, okay, we're adding energy levels. So we're adding more and more of those electron rings. So adding more energy levels. Okay, so adding more and more electrons which would definitely make the atom bigger. And then also the shielding is pushing. So shielding is pushing electrons further. Okay, ionization energy, that is simply energy needed. So energy needed to remove an electron. So just the energy needed to remove an electron. So as we go across a period, it is going to increase. Okay, so if we're adding more protons, which are pulling those electrons in tighter, it's going to take more energy to take one of those from those protons. Then as we go down, it is going to decrease. Okay, so adding more and more energy levels, electrons are getting further and further away from the nucleus. There's not as much pull on them, so it's a lot easier to come and grab one. Okay, so as we go across, more protons pull electrons closer. Okay, which basically makes it harder to steal. So more protons pull electrons closer, which basically means it's harder to steal. And then as we go down, more energy levels. So more energy levels. Electrons are further away. So electrons are further away. If they're further away, that makes them a lot easier to take. So it doesn't take as much energy to grab those. So easy to take. Okay, electronegativity. So this is just the ability of an atom to steal an electron. So ability of an atom to take an electron from another atom. Okay, so this has a lot to do with valence electrons. So remember that perfect number was 8. So when you have atoms that are getting close to that 8, okay, so they're needing just 1 or 2 more and stuff. So their ability to steal is going to be a lot higher because they want that 8. So as we go across to the right, it's going to increase. So the same thing as ionization energy. And as we go down, it is going to decrease. Okay, so the reason why. Okay, so if we're adding more protons, oops, let me fix that real quick. So we're adding more protons, basically pull on electrons from another atom. Okay, so we have more protons that are pulling in its own electrons tighter, and it can even reach outside of itself and grab electrons from another atom. And then as we go down, it's going to decrease because more electrons, okay, are going to shield. And I cannot write today. More electrons are going to shield the pull of the protons. Okay, so before I go into ionic radius, I'm just going to go back up to the periodic table just to explain that again, so just briefly. So let me clear that up. Okay, let me just tidy this up a little bit. Okay, so atomic radius, I'm going to do a different color for atomic radius. Atomic radius is the only one that gets bigger as you go down to the left. Okay, which makes sense. Helium is going to be a lot smaller than francium. Okay, so atomic radius gets bigger as you go down to the left. Okay, ionization energy and electronegativity are going to get bigger as you go up to the right. Okay, so that's the easiest way to remember this, is atomic radius gets bigger as you go down to the left, which makes sense. So just look at the periodic table and look at helium versus francium. Okay, helium's very tiny. Then ionization energy and electronegativity are going to be bigger as you go up to the right. Okay, so now let's go back down and we'll finish it. So ionic radius is just simply the size of an ion. Okay, and trends across a period, trends across a group. The big thing with ionic radius is it just depends on the number of electrons. Okay, so I wrote those across both boxes because it's not really based on the periodic table. We're starting to look at the number of electrons. So if they're all the same number of electrons, we rank them based on charge. Okay, so ionic radius, so when you're dealing with same number of electrons, so same number of electrons, negative is bigger. Okay, negative is bigger because if you have a negative charge, that means you gained electrons. If you're gaining electrons, your size is going to get bigger. Positive is going to be smaller. Okay, because positive means you lost electrons. And you now have more protons than electrons. Okay, so if they all have the same number of electrons, you just rank them based on charge. Negative being the biggest, positive being the smallest. Okay, so if they all have the same charge but different number of electrons, then just rank them based on size. Okay, so like if I had up here, let's go back to the periodic table. Say I have oxygen with a -2 charge, and then I have cesium with a +1 charge. Okay, so typically if they had the same number of electrons, you would rank them based on their charge. But we can see that oxygen is definitely going to be smaller than cesium, even though it has a -2 charge. So just make sure if they have the same number of electrons, then just rank them by size. I'm sorry, if they have the same number of electrons, you rank them by charge. And then if they don't, okay, if they all have the same charge, just rank them based like atomic radius. Okay, so let's go back down. Okay, so you're going to use your periodic table for this because this would take forever if I were to go back and forth and find these. But I will explain how you would rank them. Okay, so atomic radius, and we want lowest to highest. So smallest to biggest, so that means you're going to go down to the left. Okay, so you're going to need your periodic table so you can pause. You can pause as you want if you want to find them and then look at the answers on the video, whatever you need to do. Okay, so oxygen is going to be the smallest. It's the furthest up to the right, followed by sulfur, then arsenic, and then SB. Okay, so the same one, we're going down to the left. So boron is going to be the smallest, followed by aluminum, followed by tin, followed by lead. Okay, ionization energy. So remember that is the energy needed to remove an electron. That gets bigger as you go up to the right. Okay, so that's what you're going to do. You're going to rank them based going from bottom left to top right. So calcium would be the lowest, then zinc, then carbon, then nitrogen. Then if you go down to the next one, cesium would have the lowest energy, followed by strontium, then selenium, then chlorine. All right, so electronegativity, that was the ability to steal an electron. So it's going to get higher as you go up to the right. Okay, so you're going to start at the bottom left and work your way up to the top right. Okay, so that means cesium is going to have the lowest, and then followed by Sn, then As, then S. Moving on to the next, iodine is going to have the lowest, followed by bromine, then sulfur, then oxygen. Okay, going back to ionic radius. So, if electrons are equal, okay, rank by charge. If not equal, just go by size. Okay, so if we look up at the periodic table, so K+, CS+, and Li+. Okay, so let me clear this up a little bit. So K+, CS+, and Li+. So even though they all have the same plus charge, okay, you're just going to rank them based on size at this point because they don't have the same number of electrons. Okay, so lithium is definitely going to be the smallest, followed by potassium, and then cesium. Okay, so let's go back down. Okay, so Li would be the smallest, so Li+, followed by K+, then CS+. Okay, so now if you look at magnesium 2 plus, N minus 3, and then F minus 1. So magnesium normally has 12 valence electrons, but since we're missing 2, okay, so it's going to have 10 electrons. Nitrogen normally has 7, okay, but it gained 3, so that means it also has 10. And then fluorine normally has 9, but it gained 1, so this one also has 10. So they all have 10 electrons. So now we're going to rank them based on charge. Okay, so we're going from smallest to biggest. So remember, positive is smaller, negative is bigger. So that means Mg2 plus is going to be the smallest, followed by F with a minus 1. That's the next biggest. And then my biggest would be nitrogen with a minus 3 charge. So positive is smaller, negative is bigger. Okay, ionization energy. So again, we're going up to the right, smallest to biggest. So that is going to start off with francium going to be the lowest, then aluminum, and then phosphorus, and then oxygen. Okay, next one we're going to go into is Ba. Okay, Ba is going to be the lowest, followed by Sr, then Na, then Li. Okay, electronegativity. So again, we're going from smallest to largest, so it's going to be up to the right. So it's going to be K, Ga, Si, then N. Okay, so the next one is going to be Sn, Ge, P, and then N. Okay, so again, if you need to pause those before I write down the answers, so that way you can look for yourself, go for it. It would just take too long for me to find all these on the periodic table and scroll back and forth. Okay, atomic radius. So atomic radius gets bigger as you go down to the left. Okay, so you would start at the top right. So you would start off with fluorine, so F, then Cl, then arsenic, As, and then lastly W. Okay, the next one would be lithium, followed by sodium. Okay, then potassium, then rubidium. Okay, ionic radius, so we're going to rank based on charge. So if they have this, so we're going to look at the charges here. So we're only dealing with one element, so we're just going to rank it based on charge. So we're going smallest to biggest. Okay, so that means As with a minus 1 charging the smallest, followed by As with a 2 minus, then As with a 3 minus, and then my biggest one is going to be As with a 4 minus. Okay, looking at the next one, we have potassium with a plus charge, sulfur with a minus 2 charge, and then phosphorus with a minus 3. Okay, so these are all going to have the same number of electrons. So that means K plus would be the smallest. So this one, we actually kind of gave it to you in the right order. S with a minus 2, and then lastly, P with a minus 3. Okay, so you can go back through that if you need to. All right, so let's go over real quick the groups and their characteristics. So alkali metals. Okay, so that's going to be that group 1/1a. Okay, so these are going to have 1 valence electron. They are never found alone. Okay, which means they're very reactive. Okay, so since they're never found alone, that means they're very reactive. So they like being bonded with people. Sorry, not with people, with other elements. Okay, especially with water. Okay, it can be violently reactive with H2O. Okay, so they're soft, more easily cut. Okay, and then lastly, they are more reactive as you go down a group. So as you go down the group, they're just more reactive. Okay, so alkaline earth metals is going to be the one right next to it. So that's going to be that group 2/2a. Those have 2 valence electrons. They're also never found alone. Okay, so which means they're going to be reactive, but they are just less reactive than group 1. Okay, and these are going to be a little more... Uh-oh, don't know what I did there. There we go. Okay, so they're going to be less reactive than group 1, and then they're just going to be slightly more shiny and harder. Then you have transition metals. So remember, that was where you started on that D group, and then you started going towards the staircase. Okay, so transition metals, they don't really follow common patterns. So do not follow common patterns. Okay, and then their valence electrons vary. So that's why we had to do the whole Roman numeral thing. So I'm going to put that in parentheses. Roman numerals. Okay, so their valence electrons can vary. Unlike group 1 and group 2, okay, which their charges are stuck at +1 and +2. Okay, transition metal charges and oxidation numbers vary. So that's why we did the Roman numerals. Okay, so halogens is going to be that second to last group. So that is going to be the group 17/7a. Okay, so these are going to have the 7 valence electrons. So they're real close to that octet. So 7 valence electrons. So they are very reactive. Okay, so the reason why is because they have 7 valence electrons. They only need 1 more to make 8. So they're going to be very reactive and try to bond with other people and take an electron. So they're normally found in diatomic pairs. So found in diatomic form. Diatomic, so di just means 2, so that just means pairs. Okay, and then a lot of your salts are going to be made up of halogens. Lastly is going to be noble gases, so that's going to be your group 18/8a. Okay, so it has 8 valence electrons. Okay, so it's reached its octet. So it is not going to be reactive at all, so it does not react. Okay, it has its 8, so it doesn't need to react with anybody. It doesn't need to bond. They're good on their own. All of them are going to be gases. And then most are going to be colorless and odorless. Okay, so that's just kind of a brief going over the main groups that we deal with. All right, so we're going to kind of try to breeze through these. Okay, so you have a group and you have a period. Okay, so a group is going to be your vertical column. So vertical column. So that means going up and down. Okay, they have the same valence electrons, which means they have common characteristics. If you have the same number of valence electrons, you're going to have the same kind of characteristics. Okay, kind of barged into my period side over here. Period, there's not a whole lot to it. Period is just basically your horizontal rows. So going left to right. And they don't have any common characteristics. So no common characteristics. Okay, Mendeleev, how did he arrange the periodic table? Why is he important? And what did he predict? Okay, so his big thing is he arranged the periodic table by mass. Okay, so he was one of the first to actually create a useful periodic table. So that's his big thing. Okay, so he was one of the first to develop a useful periodic table. Okay, so he started off, he was one of the first, so he arranged it by mass. So that was the best way he figured it out. But in his time, he knew that he was not going to be able to find them all. Okay, so he left gaps okay, for future discoveries. Okay, so he knew there was other elements, but he was just not able to get to those, so he left gaps to basically fill in as we went on with time. Then you had Moseley come along in the early 1900s, and so he arranged it by atomic number. Okay, so this helped out a little bit more with the organization of it, so we ranked it by atomic number. Okay, number 4. How does the ionic radius of a typical anion compare with the radius of the corresponding neutral ion? Okay, so an anion is bigger, okay, because you gained electrons. Okay, so again, I'm just doing this very rudimentary and stuff, so if you want to explain it better, you can. So an anion is bigger than the neutral one because you gain electrons. So therefore your radius is going to increase. Okay, a cation is smaller because you lost electrons. So now you have more protons than electrons. So your radius is going to get smaller. Why do elements in the same family? So family basically just means group. Generally have the same properties. So like we were talking about earlier, if you have the same valence electrons, you have the same kind of characteristics. 7, why are electrons in the outer shell of an atom important? So those are our valence electrons, so those really help determine bonds with other atoms. So help determine bonds with other atoms. And then lastly, describe the properties of ionic compounds. So ionic is basically a metal and a non-metal forming a bond. Okay, so they're going to have, oops, let me fix that real quick. Okay, so we're going to have high melting point and boiling point. Okay, so high melting / boiling points. The reason why is because an ionic bond is a very strong bond, so you would need more energy to break it apart. Okay, they're going to be hard and brittle. Okay, so when they're solids, they're hard and brittle. And they're also non-conductors whenever they're solids. So that means not very good for electricity when they're solids. However, most are soluble in water. So basically mean we can break it down in water. Okay, so when it's dissolved, so when we break it down in water, we dissolve it. Okay, these free ions will float and conduct electricity. Okay, you ought to know these as electrolytes. And then lastly, they're going to form lattice structures. Okay, lattice structure is just basically it's repeating crystalline solid. Okay, so these are very basic answers on here. On the keys, it's going to be a little bit more in depth, but I'm trying to save time on this video, so we're just kind of going through the main points. Okay, so good news, we're getting closer and closer to being done with the writing part. We can get into practice. Okay, so monoatomic cation. Okay, so mono means one. Okay, this is just going to be a single atom with a positive charge. Okay, so that would just be something like Na plus, Ca2 plus. Okay, so that's a monoatomic cation. So mono just means one element, so it's by itself. Again, monatomic anion, so again, we're just dealing with one. So a single atom with a negative charge. Okay, so that would be something like fluorine with a -1 charge or O2 minus. Okay, polyatomic. So poly means many. Okay, so this is an ion consisting of 2 or more atoms. Okay, so that's like that list we gave you, so you will need that list here in a second when we're doing those practices. Okay, so that'd be something like phosphate, which is PO4 with a 3 minus, or nitrate, which is NO3 with a -1 charge. Okay, so that's a polyatomic ion. Oxidation number is just a fancy word for the charge of an atom. Okay, so that's like +3, -2. Okay, so that's just the charge, so nothing fancy. Okay, transition metals. Okay, so this means they are metals that can have more than one oxidation number. Okay, so they can have more than one charge. So therefore we use Roman numerals whenever we're writing out the names. Okay, so if I had something like this, so Fe with a +3, if I were to write that out, that would be iron 3. So 3 I's. Okay, so we're going to use Roman numerals to indicate the charge of a transition metal. So now we're going to go into plenty of practice. What you'll need is your periodic table, okay, and your polyatomic list. Okay, so if you need to pause it and grab that, you can. Okay, so we're going to write the chemical formula and chemical name or split them up if we need to. Okay, so we're going to start with the first one. So Ti plus 5 and N minus 3. We can tell right now that they are not balanced. So if you want to do the crisscross thing, you can. So that means I would take the 3 to Ti and I would take the 5 to N. So this would just be Ti 3 and N5. Now you need to look up, is titanium a transition metal? If it is, we need a Roman numeral in the name. So it is. So we're going to write out titanium. Okay, and this titanium has a charge of 5, so that means we're going to put 5, okay, or V. Okay, let me fix that real quick. The whole thing was pretty poorly written. So titanium 5. And then our anion, remember we changed our anion's name, we end it with IDE if it's just by itself. So if it's just nitrogen by itself, it's going to be nitride. Okay, so whenever it comes to breaking things apart, I always like to start off with the anion first because you can just look at the periodic table or just look at your polyatomic list and just go from there. Okay, so NO3, if you look on your polyatomic list, that is nitrate, and that has a -1 charge. Okay, and if you look up calcium on your periodic table, that is in group 2. Calcium has a charge of +2. Okay, so if we were out the name, this would just be calcium. Calcium is not a transition metal, so we do not need a Roman numeral. And this would just be nitrate. Okay, next one, nickel 2 carbonate. So nickel has abbreviation of Ni. And this 2 right here tells me the charge of it. So this would be nickel with a +2. Then you're going to look up carbonate on your polyatomic list. That is CO3 with a -2. Okay, so now we want to bring it together. It's already balanced, so all you got to do is just put it together. So NiCO3. That's it. Okay, so let's do our next one. We have aluminum hydroxide. So OH is on your polyatomic list. So that is OH with a -1. And if you look up aluminum in your periodic table, so that's one of those 3 exceptions on our transition metal, and it always has a charge of +3. Okay, so even though aluminum is a part of that transition metal group, it always has a charge of +3, so therefore we do not need a Roman numeral. So this would just be aluminum hydroxide. Okay, Sr2 plus, HCO3 minus, so we can tell right now it is not balanced. Okay, so I only need 1 Sr, but I'm going to need 2 of these bicarbonates. So I'm going to put the whole thing in parentheses and then put a 2 outside of it. Okay, so Sr is going to be strontium. That is not a transition metal, so we don't need a Roman numeral. And then HCO3 is on your list, your polyatomic list. That is bicarbonate. Okay, next one. I can see that this is not balanced, so I'm going to need 3 hydrogens to balance out that 1 PO3. Okay, so now I have a +3 charge to balance out my -3 charge. Okay, so this is just going to be hydrogen. Okay, so PO3 is going to be phosphite. Okay, so we're going to break these both up. So SO4 on your list is sulfate, so that's SO4 with a -2. And then NH4, if you look that up, that is NH4 plus. Okay, so you could just look at your list for those two and just break them apart. Okay, so NH4 is ammonium. And SO4 is going to be sulfate. Okay, next one we have MgO. So remember, I usually start off with my anions. If you just look up oxygen on the periodic table, it has a charge of -2. Okay, and if you look at magnesium, it has a charge of +2. Okay, magnesium is not is not a transition metal, so it does not need a Roman numeral. Okay, so next one, if you break up the anion first, so C2H3O2, and that is going to have a -1 charge. That is acetate on your polyatomic list. And aluminum is going to have a charge of +3. So this is going to simply just be aluminum acetate. Okay, Hg plus, NO3 with a -1, already balanced, so just put them together. So HgNO3. Okay, Hg is going to be mercury. Okay, mercury is one of those transition metals. Okay, so it does need a Roman numeral, so we're just a +1. So that means we're just going to do 1I. So mercury 1, and NO3 is nitrate. Okay, next one I can see it's already not balanced. So I'm going to need, you can do the crisscross if you want, take the 3 to the K. So I'm going to need 3 Ks and only 1 P. This is just going to be potassium phosphide. Okay, aluminum nitrite, so I'm going to look up on polyatomic list, nitrite. Okay, so that's going to be NO2 with a -1 charge. Aluminum on the periodic table has a charge of +3. Okay, it's not balanced. Okay, so that means I only need 1 aluminum. So if you do your crisscross, I only need 1 aluminum. But I'm going to need 3 of these nitrites. So I'm going to put the whole thing in parentheses and put a 3. Okay, Ag3N. Nitrogen on the periodic table has a charge of -3. And Ag is one of those ones that's stuck at a charge of +1. Okay, so Ag, since it always has a charge of +1, it does not change. You do not need a Roman numeral. So that's just going to be silver nitride. Okay, calcium phosphate. So if you look at phosphate on your list, PO4 with a -3 charge. Okay, calcium is going to have a charge of +2 on your periodic table. Okay, so you can do the crisscross method. So that means I need 3 calciums, and I'm going to need 2 phosphates. I'm going to put phosphate in parentheses and then put a 2 outside. Okay, Rb2O, O with a -2 charge. Okay, and you look up Rb on the periodic table as Rb. Let me fix that. Rb with a +1. So it is not balanced, so I'm going to do the crisscross. Well, I already did it in the formula. Okay, so we just got to spell it out. So there's going to be rubidium oxide. Okay, Pb4, OH -1, so we can tell it's not balanced, so you can do your crisscross. So I'm only going to need 1 Pb, but I'm going to need 4 of these hydroxides. Okay, so Pb is lead. That is one of our transition metals, so even though it can only be 2 or 4, we still need a Roman numeral. Okay, 4 is going to be IV, and then this is going to be hydroxide. Okay, next one, SnF2. So I'm going to start with my anion. So if you look up fluorine, it has a charge of -1. Okay, so that means if I have got two of those, that has a charge of -2 for my fluorines, but I only have one Sn. Okay, so that means my charge for Sn has to be a +2. Okay, you can try to, so that's a reverse crisscross. So I would take that 2, bring it up to the Sn, and take the 1 Sn and bring it up to the F. Okay, so Sn is going to be 10. That is one of my transition metals, so we do need a Roman numeral. So the charge of 10 is going to be 2, so that's 2 I's. So 10-2 fluoride. Okay, calcium sulfite. So I'm going to start off with my anion. So sulfite is on your list. That is SO3 with a -2. And calcium has a charge of +2. So it's already balanced, so you just put them together. So CaSO3. Okay, then we have NaBr. So you can just look up these on the periodic table. Br has a charge of -1. Na has a charge of +1. And this is just simply sodium bromide. Okay, magnesium perchlorate. So I'm going to start with my anion. So perchlorate is going to be ClO4 with a -1 charge. In magnesium, you can just look at that on the periodic table as a charge of +2. Okay, I can tell that they're not balanced. So you can do your crisscross. I only need one magnesium. But I'm going to need 2 of those perchlorates. So ClO4 in parentheses with a 2. Okay, so we're getting there. Okay, BeCl. So I can tell right now it's not charged and not balanced. So we can crisscross the charges. So this is BeCl2. And this would just be beryllium chloride. MgNO2. Okay, so NO2 is going to be nitrite. That's on your list. So with a -1 charge. And Mg is on your periodic table as +2. And this is just going to be magnesium nitrite. Okay, copper 2 bromide. Okay, so bromine has a charge of -1. Copper is Cu, and that 2 right there tells me the charge of it, so that's +2. And I can tell that's not balanced, so I'm going to do my crisscross. So I only need 1 copper, but I need 2 bromines, so CuBr2. All right, so next one. Oxygen has a charge of -2. K has a charge of +1. You could just look on the periodic table for that. This would just be potassium oxide. Pb2 plus, S -2, it's balanced, so all I gotta do is put it together. So PbS. Okay, Pb is going to be lead. That is a transition metal, so we need to write down the Roman numeral for the charge. So lead 2, and then just sulfide. Okay, Ca +2, PO4 with -3. Not balanced, so I'm going to do the crisscross. So I would need 3 calciums. I'm going to need 2 of these PO4, so I'm going to put the whole thing in parentheses with a 2 outside of it. So this would just be simply calcium phosphate. So that is on your list. Iron 3 chromate. So iron 3, so it tells me iron Fe has a charge of +3. Okay, chromate is on your list. That is Cr. Oops, let me fix that. CrO4 with a -2. It's not balanced, so I'm going to go ahead and do the crisscross. So I need 2 irons. I'm going to need 3 of these chromates. Okay, next one, Na2CO3. So CO3 is on your list. That is CO3 with a -2 charge. Sorry. Na is on your periodic table. That is just simply +1. So this will be sodium. And CO3 on your list is going to be carbonate. Okay, it says aluminum acetate. So acetate is on your list. So that's C2H3O2 with a -1. And aluminum has a charge of +3. Not balanced. So I'm going to do my crisscross. So I only need 1 aluminum. But I'm going to need 3 of these acetates. I'm going to put the whole thing in parentheses with a 3. Zn plus 2 with the NO3 minus 1. Not balanced, so crisscross. So 1 zinc. And I'm going to need 2 nitrates. Okay, so zinc is in that kind of transition metal group, but it's always stuck at a plus 2 charge, so we don't need a Roman numeral. Okay, so this would just be zinc nitrate. Al4C3. Okay, so carbon on your periodic table has a charge of -4. Okay, and aluminum has a charge of +3. You could do the reverse crisscross there if you wanted to. I usually just look at the periodic table. So this would just be aluminum carbide. Okay, aluminum is always stuck at +3, so it did not need a Roman numeral. Okay, calcium hydroxide. So hydroxide's on your list, so that's OH minus 1. Calcium on your periodic table has a charge of +2. So it's not balanced, so I only need 1 calcium, but I need 2 hydroxides. So OH with a 2. Okay, Ag2CrO4. Okay, so CrO4 is on your list. That is chromate, so -2. And Ag is on your periodic table, always has a charge of +1. Okay, so always has a charge of +1, so it's just going to be silver, no Roman numeral. Okay, CrO4 is going to be chromate. Lead 4 chloride. Okay, so chloride just means it's chlorine by itself. Lead 4, so that tells me it's going to be lead, so Pb with a +4 charge. So it's not balanced. So do the crisscross, only need 1 Pb, but I'm going to need 4 chlorines to be balanced out. Okay, CaBr2, so Br with a -1 charge. Calcium with a +2 charge, just on the periodic table. Okay, so calcium, and it's going to be bromide. Okay, so it's just bromine by itself, so you're going to end it in IDE. Mn for OH minus, so we can tell it's not balanced. So crisscross, I only need 1 Mn, but I'm going to need 4 of these hydroxides. Okay, so Mn is manganese, so watch out, it is not magnesium. Manganese, and that is a transition metal. Okay, so we're going to need to put the charge. So manganese 4, so that's IV, and this is hydroxide. Oops, kind of scrolled down there on me. Okay, getting there almost to the end. Okay, so Cn is on your list. That has a -1 charge. Okay, that is cyanide. And then aluminum has a charge of +3. Okay, so this is going to be aluminum cyanide. Okay, iron 2 acetate, so acetate's on your list, so that's C2H3O2 with a -1. And iron 2, so that's Fe with a +2 charge. Okay, so it's not balanced. I'm going to do my crisscross, so that means I only need 1 iron. But I'm going to need 2 of these acetates to be balanced out. Okay, CaO. O is -2. Calcium is +2. Okay, and this would just be simply calcium oxide. Okay, ammonium phosphide. So phosphorus on your periodic table is a -3, and ammonium is on your list. That is NH4 with a +1 charge. Okay, so we can tell it's not balanced. So you can do your crisscross. So that means I'm going to need 3 of these ammoniums to balance out 1 phosphorus. Okay, so we're almost there. So the last thing is oxidation numbers. Okay, so when you have an element by itself, so like an A, you see that there's no charge up here. So that basically means there's 0 charge. So these are easy. So it's just going to be Cl with 0 charge. That's it. Okay, so we'll go ahead and do the same for this one. C is going to have no charge. Okay, so those are 2 kind of gimmies. Okay, so I'm going to go over how I kind of do this. So first thing I got to look at is there a charge? Okay, if there's no charge, that means we have to set it equal to 0. So what I do is I give myself some space. So into O3. Okay, so I'm going to find the charge of each one. And then I'm going to find the total charge. So charge of each right here, and then total is going to be down here, and I'm going to set it equal to 0 since there was no charge. Okay, so always start with oxygen first. Oxygen has a charge of -2 that does not change. So 3 times -2 is going to give me -6. So I need to know what -6 gives me 0. Okay, so that's going to be 6. Okay, so now I need to find the charge of each nitrogen. So if I have 2 of them, 6 divided by 2, that means each one is going to have a charge of +3. So my answer would be N equals +3, O equals -2. Okay, so let's do another one. So there's no charge, so that's a 0. So I'm going to give myself some room. So H2SO3, draw my line, and I'm going to set it equal to 0. So O has a charge of -2 always, so we're going to start with oxygen. Okay, so I've got 3 of them, so that's -6. Okay, I'm going to save that sulfur for last. Whatever's attached to that oxygen, I'm going to save for last. Okay, so I'm going to go and do hydrogen next. Hydrogen always has a charge of +1. So I have 2 of them, so that's going to be a total charge of 2. So 2 plus blank minus 6 equals 0. Well, that's going to be 4. And since I only have 1 sulfur, that means this charge of that sulfur has to be +4. So your answer would be H equals +1, sulfur S equals +4, and O equals -2. Okay, so same thing. I'm going to give myself some room. Okay, there's no charge here, so I'm going to set equal to 0. Start with oxygen. Oxygen has a charge of -2. So 2 times -2 gives me -4. So I need to know blank -4 gives me 0. That is going to be 4. And since there's only 1 manganese, that would have to have the same charge of 4. So that means manganese has a charge of +4. Okay, so next one, I'm going to give myself some room. So I have 1 zinc. Okay, so this is where you got to watch out for parentheses. This 2 right here means I have 2 chlorines. And then I have 3 oxygens on the inside of the parentheses, so 2 times 3 means I have 6 oxygens. Okay, there's no charge, so I'm going to set it equal to 0. I'm going to start with oxygen. Oxygen has a charge of -2. So 6 times -2 gives me 12, -12. I'm going to save chlorine for last. Zinc has a charge of +2 if you look on your periodic table. And since there's only 1, that's going to be a total charge of 2. So 2 plus blank -12 equals 0. So that's going to be 10. So 2 plus 10 minus 12 equals 0. And since there's 2 chlorines, I'm going to divide 10 by 2. So that means each chlorine has a charge of +5. So Zn equals +2, Cl equals +5, and oxygen equals -2. Okay, part G, we just did that one. That was the same thing in part E, so I'm not going to worry about that one. Okay, KClO, KClO. Okay, there's no charge, so I'm going to set that equal to 0. Start with oxygen. Oxygen has a charge of -2, and there's only 1. So that's going to be -2. Then I'm going to go over to potassium. Potassium has a charge of +1, and since there's only 1 of them, okay, that means a charge of 1. So 1 plus blank -2 equals 0. Well, 1 plus 1 minus 2 equals 0. So there's only 1 chlorine, so that means that chlorine has to have a charge of +1. So K equals +1, Cl equals +1, and O equals -2. Oops. Okay, so last strip. So we're almost there. So P2O3, give myself some room. There's no charge there, so I'm going to set equal to 0. Oxygen has a charge of -2. So 3 times -2 gives me -6. So what -6 gives me 0? So that's going to be 6. And since I have 2 phosphoruses, I'm going to take that 6 and divide it by 2. So that means each one has a charge of plus 3. So phosphorus has a charge of plus 3. Next one, Mg. I have 2 I's because of that parentheses, so 2 I's, and I have 6 oxygens because of that parentheses. So there's no charge, so I'm going to set that equal to 0. So oxygen has a charge of minus 2. 6 times minus 2 gives me minus 12. Mg has a charge of plus 2 on the periodic table. So 2 plus blank minus 12 equals 0. That's going to be 10. And since there's 2 iodines, I'm going to divide 10 by 2, so that means each one has a charge of plus 5. So iodine has a charge of plus 5. Next one, I have 3 Mgs. I have 2 arsenics. And I have 8 oxygens. Okay, so watch out for those parentheses. There is no charge up here, so I'm going to set equal to 0. 8 times negative 2 is going to give me minus 16. Mg has a charge of plus 2 on the periodic table. So 3 times 2 is going to give me 6. So 6 plus blank minus 16 gives me 0. So 6 plus 10. And since there's 2 arsenics, I'm going to divide that 10 by 2. So that means each one has a charge of plus 5. Okay, so Mg equals plus 2. As equals plus 5, and O equals minus 2. Okay, next one we have Mg. I have 2 oxygens and I have 2 hydrogens. Okay, there's no charge there, so I'm going to set it equal to 0. Start with oxygen. So, oxygen has a charge of minus 2, so that's going to be minus 4. Hydrogen has a charge of plus 1. Okay, so that's plus 2. And then magnesium also has a charge of plus 2. Okay, so 2 minus 4 plus 2 equals 0. So this one was just kind of a more simple one. We weren't finding anything really different there. That was just all on the periodic table. So Mg equals plus 2. O equals minus 2. And H equals plus 1. Okay, next one I have NO3 with a minus 1 charge. So NO3. Okay, but I do have a charge there. There's a minus 1, so I'm going to set that equal to minus 1. Okay, so you got to watch out for that. If there's a charge there, that's what we set it equal to. So oxygen has a charge of minus 2, so 3 times minus 2 gives me 6. So what minus 6 gives me negative 1, so that's going to be 5. And since there's only 1 nitrogen, nitrogen is going to have a charge of plus 5. So N equals plus 5, O equals minus 2. Okay, next one, I have H2, 1S, and then O4. Okay, there's no charge, so I'm going to set it equal to 0. So 4 times minus 2 gives me minus 8. Hydrogen has a charge of plus 1. There's 2 of them, so there's a total charge of 2 for hydrogen. So 2 plus blank minus 8 equals 0. So 2 plus 6 minus 8 equals 0. There's only 1 sulfur. So that means that's going to have a charge of plus 6. So sulfur has a charge of plus 6. Last one, I have C2O4. And I have a minus 2 charge. So I'm going to set it equal to minus 2. So oxygen is a charge of minus 2. So 4 times minus 2 gives me minus 8. So what minus 8 gives me negative 2? That would be 6. And then I have 2 carbons, so 6 divided by 2 means each one has a charge of plus 3. Okay, so hopefully that kind of helped out. So feel free to rewind and then let us know if you have any questions.